Hi, I'm Richard Kiles, a principal consultant at General Data Tech. I wanted to take a few minutes to discuss network namespaces in more detail and provide some real-world examples of how I've used them in the past. We'll also discuss how this technology is used within containers, specifically in regards to Docker. About a year ago, I had a customer who was performing network tests on some upstream equipment. To do so, they were trying to run two instances of Apache on a Linux server with two network interfaces. Each interface was connected to the same Layer 2 broadcast domain. In other words, they were connected to the same logical network. The customer was experiencing problems with outbound traffic only traversing one of the interfaces. This problem is due to the simple fact that a system can only have one default gateway defined in its routing table. Apache can be configured to listen on a particular interface, and we can use DNS to send inbound traffic to specific IP addresses. But outbound traffic will always be sent over a specific interface based on the routing table, and the interface defined with the default gateway in this configuration was ETH0. An efficient solution to this problem was to create a new network namespace for one of the Apache instances. Network namespaces allow processes to run in an isolated environment within a Linux kernel. It also creates a separate instance of the networking stack, including its own routing table. By creating a new network namespace, I was able to isolate the second instance of Apache, bind ETH1 within that namespace, and configure the network adapter as the interface for the default gateway, all without impacting the other Apache instance or routing table running on the same host. The customer was then able to ensure traffic for a specific Apache instance would traverse both inbound and outbound over a dedicated network interface. Now, it's important to note that when you bind a resource to a namespace, no other namespace can have access to that resource. This includes the default namespace, often referred to as the root namespace. In other words, if I run IP-link show within a network namespace, I will only see the interfaces bound to that namespace. Conversely, if I run IP-link show on the root namespace, I will only see interfaces that are not bound to a namespace. Those bound resources disappear from the system context until you destroy the namespace. Docker is using a similar approach with network namespaces to allow connectivity for containers. The main difference is that instead of binding a physical interface to a namespace, as described with the previous example, Docker is leveraging virtual Ethernet interfaces, otherwise known as vEths. As discussed in my previous video, Docker creates a Linux bridge named Docker 0 that allows connectivity between the host and its running containers. IP table rules then allow outbound connectivity between the bridge and the host network interface. Inbound rules follow the same basic structure when we expose ports from a container. Since we do not have enough physical adapters on a host to bind a dedicated interface to each container, a new vEth, our virtual Ethernet adapter, is created on the host and peered between the container's Ethernet adapter. This allows the container running within an isolated network namespace to connect to the Docker 0 bridge running on the host. Since the container is isolated in its own namespace, it does not have the ability to directly connect to a shared Docker bridge, which is why Docker creates a dedicated vEth adapter for each container that will be connected to the bridge, and then peers it to the adapter in the container's namespace. Let's take a look at this in a little more detail. I'm currently connected to a Linux server that's running Docker. If we do an IP-link show, you'll see that we have our Docker 0 bridge down at the bottom. I can also do an IP adder show, and we can see that the IP address that's currently assigned to this bridge is 172.17.0.1. We can even get more information about the bridge itself by doing a brctl, our bridge control, show max Docker 0. As you can see, there are currently no MAC addresses that are associated with this bridge. So let's run a container and see what happens. Let's do a docker run -d, and we'll run this in the background. And we'll use an existing image that I have that is running a Flask server. Flask-test. Now, if we go back and do a IP link show, you'll see that we now have a new veth. This is the peer from our host operating system, or our root namespace, that is linked or peered to our Docker instance. Now if I do a brctl show max on Docker 0, you'll now see that we have our veth MAC address as well as another non-local MAC address listed on the Docker 0 bridge. We can verify that this is the MAC address of our container by pulling the container ID, docker ps, and we'll take this container ID and run a docker exec to execute a command interactively on our container. We're going to run IP adder show. As you can see, our eth0 interface has the corresponding MAC address of 0002 that we see here in our show MAC table. So our Docker bridge has successfully learned both the veth MAC address as well as the peered address that's running within the container's namespace. If you have any questions about how namespaces are used within containers, or if you'd like more information about containers in general, please feel free to contact us at General Data Tech, or take a look at any of our other videos that we have on our YouTube channel. Thank you.